So first part is introduction. The second part is magnetic field and field lines. The third part is magnetic field due to current carrying conductor. In that we will see straight conductor. Then we will see thumb rule. Then we will see conductor of the shape circular loop, and then we will see of solenoid. So straight conductor, circular loop and solenoid. These three types of conductors we will see, and then we will discuss. I think I'll cover first three part immediately here and go for solving questions. Then I will cover, no, first two part I will cover first, then go for solving questions. Then third part I will discuss and go for solving questions. And then we will discuss about the force on current carrying conductor in the magnetic field. And in motor, you have to just know the principle. Magnetic induction is not there. Then in generator, you have to just understand the principle and use only these two parts. As per the syllabus, it is principle and use. These two parts only you have to study. And the last we will study about the domestic electric circuit. So let me begin with the first part. First is introduction. Now, a scientist Oersted discovered that electricity and magnetism are related to each other. So he discovered this thing. Magnetism and electricity have got some relations. What was the relations? He saw magnetic needle gets deflected when an electric current passed through metallic wires nearby. That was found by Oersted. And because of his invention, the unit of magnetic field strength is named after his name as Oersted. And Oersted research created technologies like radio, television, fiber optics, and so on. So this was just an introduction of this topic, and let us go to the next one. Now you have to understand the magnet and magnetic lines, or magnetic field and field lines. We know that compass needle deflects when brought near another magnet or conductor carrying electric current. So what is compass needle? Compass needle, it is a bar magnet. It is a bar magnet and it points towards the north. It always points towards the north. So one end pointing towards the north, and that is called as north pole or north seeing. The another end pointing towards the south, it has got two ends. So that is called as south pole or south seeking. So what we observe that if we take two magnets, then like poles repel each other. North pole repel each other, and unlike poles attract each other. If you bring north and south together, it will attract each other. That is the characteristics of the magnet. So we observe the magnetic lines. How? You take iron filings. Iron filings is nothing but iron powder. You must have seen grinding in the workshops where fabrication is done. So that is called, the powder that is formed is iron filing. So when you put iron filing near the bar magnet, these iron filings align along the lines. See, these are the field lines. So iron filings also align along these field lines. So that shows that there is magnetic field lines and they are in this fashion. So you see they are thick at the south pole and north pole. That is why the magnetic field is maximum at north pole and south pole. And next one is near to the bar, they are thickly populated. So near to the bar is the next strength. And as we move away from the bar, these magnetic lines, they become thinner and thinner. And that is why as we move away from the bar, the magnetic field strength is lesser and lesser. So with that we will see next magnetic field. The region surrounding the magnet in which force of the magnet is detected is said to have a magnetic field. So magnetic field nothing but it's an area surrounded by the magnet where the force of magnet is detected. So that area is called a magnetic force. And then we have to understand what is magnetic lines, field lines. The lines along which the ion filings align themselves represent magnetic field lines. You see here this ion filing got aligned themselves here, so and they are called as magnetic field lines. And again I have shown you magnetic field lines drawn here over here, which shows the magnitude and direction. Magnitude meaning what? How much is the strength of the magnet, very strong or weak, that is called the strength, and that is called magnitude of the magnetic field. And the direction is from which point it starts and which point it ends, that is called the direction. So let us see the direction first. See, these field lines emerge from North Pole, and you see all these directions from North Pole, and they make a circle and emerge to South Pole. Starts from North Pole and emerge to South Pole. Similarly this side also, and similarly here they emerge from North Pole and they will go through big circles and start from North Pole and emerge into the South Pole, you see here. So direction of the magnetic field is from field of lines is from North Pole to South Pole, and inside, second point is inside all these magnetic field lines, they are moving from South Pole to North Pole, South to North Pole, and they are parallel and uniform. Inside they are uniform and parallel. So the magnetic strength inside the bar is uniform, same throughout. Whereas outside, let us see the magnitude. So magnitude outside is more near the North Pole and South Pole, and it is more near the magnet, and as we move away from the magnet, the magnitude of the magnetic field goes on reducing. And you can draw the actual magnetic field lines using the compass needle, that we will not discuss here. Only you have to know that you can draw the magnetic field lines using the compass needle. Now you see here we are discussing in three parts. One is magnetic field due to current carrying conductor, that is a straight conductor. Then we will discuss for the, of course, right hand thumb rule, and then we will discuss for current through a circular loop. First current through a straight conductor, then current through circular conductor, and third we will discuss about current through the solenoid. These three cases we will discuss, and then we will go to the questions back. So let me start with the first thing, that is magnetic field due to current carrying conductor. Now here what happens, you take a magnetic needle and or a magnetic compass and place it like this, exactly above the line of conductor carrying current, and you see this current direction like this. So compass is deflecting north in this direction. You see this is north, and then what you do, you change the battery terminals. And you see the current will get changed. So the direction of the current will be in opposite direction, and the now deflection you will observe is in this fashion. North is going this side, so it will be opposite. It will be 90-degree opposite. You see, so that means the direction of magnetic field depends upon the direction of the current. If the direction of the current is changed, then the direction of the magnetic field is changed. That is detected by the compass needle. So this is what this diagram says. And then we will see how are the magnetic field lines in a straight conductor. For that, what is done? This is the circuit carrying the current, and this is the conductor which carries the current in the downward direction. Current through it is in downward direction. And we place a paper over here. Here's a paper, a plane, and it is seen that the magnetic field lines in a by a straight conductor, it is by a straight conductor. By a straight conductor is concentric lines. These are the concentric lines. Now the direction of magnetic field, you see, this is in the clockwise direction. I have shown it. When the current is this way. And if you see the, no, I have not drawn that. If we change the direction of the current from top to bottom, it is now. If you change it from bottom to top, then the direction of the magnetic field changes. So you see, one point you have to remember that in a straight conductor, round the conductor, the magnetic fields are concentric circles, and these concentric circles are thicker near the conductor, and as we go away, they become thinner. So that means near the conductor, magnetic field strength is more, or it is strong, our magnitude is more, and as we move away from the conductor, the magnetic field strength becomes lesser and lesser. That is, magnitude of magnetic field becomes lesser and lesser. That is, the field strength becomes lesser and lesser. So here it is written, when direction of current is changed, the direction of magnetic field is also changed. This is one point you have to remember. Second point, electric field lines are concentric circles, and they are thicker at the center and thinner as we go away from the conductor. The second point you have to remember. Third point is, as current is increased, magnetic needle deflection increases. What does it mean? That means the magnitude of magnetic field is directly proportional to the current. If the current is more, the magnitude of magnetic field is more. If the current is less, the magnitude of magnetic field is less. So that is this second point. And the third point here is, as we move away from the conductor, magnetic field strength decreases, that we have already discussed. So this is about 4 points, not more. These are just 4 points that you have to remember for magnetic field due to current through a straight conductor. And then how to determine the direction of the current and the direction of the magnetic field. As I have told you, as direction of magnetic field gets changes, as the direction of current gets changes. So how to determine these two directions? And to determine these two directions, we have got just give me 5 seconds. Yes, let me come back. That direction is given by right hand thumb rule. See, what is right hand thumb rule? Right hand thumb rule is, you see, in your right hand, you have to take a conductor carrying a current. When you hold the conductor carrying a current with a thumb in the direction of the current, then your fingers rep will give you the direction of magnetic field. Now here the fingers rep are in clockwise direction, so the magnetic field is clockwise. And suppose if your thumb is pointing in the upward direction, or the current is in the upward direction, then the magnetic field will change in the anti-clockwise direction. And this is the statement. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the current, then the fingers wrapped around the conductor is the direction of magnetic field. The magnetic field due to current through a circular loop. Now we had taken in the first case a straight conductor, and there we have seen the direction of magnetic field and direction of current is determined by right hand thumb rule. Now second case is magnetic field due to a current through a circular loop. Now what is circular loop? It's a instead of straight conductor, a conductor is bent in a circular shape like this, and current is passed through this circular loop. And what is observed here, you see at every point near the conductor, the circles are the concentric circles of magnetic fields emerge, just like that of the straight conductor. And these circles, concentric circles, will become bigger and bigger, and here they become bigger and bigger as we move away from the point. And similarly at this end also, these concentric circles will become bigger and bigger, and when it reaches at the center, these concentric circles are so big that they are almost straight lines. They are almost straight lines, you see. So this is at every point. This is at every point. That means near the conductor, the magnetic field lines are more, or magnetic field strength is more. But as we go away from the conductor, the magnetic field strength becomes lesser and lesser. So these are the points you have to remember. The field are concentric circle at each point. So I have to add here at each point around the conductor. These circles become bigger and bigger as we move away from the conductor. They become straight line at the center. And the third point is, again you see, instead of one conductor over here, one single coil or one single loop, I have taken many number of coils or many number of loops. So when many number of loops are there, it becomes a coil. Let us say the number of loops are n. So each conductor gives, let us say, certain magnetic field. If there are n number of coils, the magnetic field can become n times, because the direction of current is same, because same current is flowing through the each circular ring or each turn of the coil. So the third point is magnetic field strength is n times in a coil, where n is number of turns in a coil. Now here I have taken the coil. Coil means having many number of single loops, and supply is connected over here, and you see a plane is kept like this. Then near the conductor, lines are concentric circles. As we move away from the conductor, these concentric circle lines will become bigger and bigger, and at the center you say dash 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 dash. So dash lines, that is only a dash line at the center is a straight line. It appears as if it is a straight one. So these are the 3 points you have to remember for a field due to current through a circular loop. Now, magnetic field due to a current in a solenoid. What is solenoid? Solenoid is nothing but you wrap around the insulator a number of turns of the coil. So you see here, on top is a insulator. Over that you wind number of turns of the coil. and to this coil you supply the current through the voltage, and this is the key. What happens is that this becomes a solenoid. This coil, cylindrical coil, is called a solenoid, and solenoid is nothing but it is like a bar magnet, as I previously said during solving the questions. So bar magnet means it is exactly same as the field lines, same as the bar magnet field lines. So one becomes south pole and this becomes north pole. The magnetic field lines emerge from north pole and diverge to south pole, and the direction is from north pole to south pole. You see both the sides, north pole to south pole, and inside the solenoid the magnetic fields are from south pole to north pole, and they are straight and parallel and uniform. It is same as that of the bar magnet. So one more thing, if we place a soft iron piece inside this solenoid, this is the soft iron piece. So this is soft iron piece which is placed inside the solenoid, and when current is passed through the coil, this soft iron piece, it becomes a magnet. It becomes a magnet when current is passed through the coil. So this magnet which is formed when current is passed through the coil is called an electromagnet. It is called an electromagnet. Remember this word. It becomes electromagnet. And making this electromagnet, this principle is used in motors and generators. Okay, so with this you have to remember only 3 points. Solenoid is nothing but bar magnet, and bar magnet and solenoid is same. It has got north pole, south pole. Field lines inside the solenoid are parallels and straight lines, and they are uniform, same as bar magnet. Soft iron when placed inside the solenoid gets magnetized, and that is called as electromagnet. So this is about the current carrying conductors in various forms. And with this discussion, let us go to solve some questions, and then we will come to the force acting on the solenoid, Fleming's left hand rule, then magnetism in medicine, electric motor, electric generator, and domestic electric circuit. Now let us discuss this. Force on current carrying conductor in a magnetic field. Force is exerted on a current carrying rod when placed in a magnetic field. Magnetic field is there, and a rod which is carrying the current is brought into the magnetic field area. Then what happens? It exerts a force. It exerts a force in both directions. When the current is changed, the force exerted gets changed. When the magnetic field direction is changed, the force exerted is also changed. So you have to note down these points. The direction of the force on a conductor depends upon number 1, direction of the current, and number 2, direction of magnetic field. Now the magnetic field of the force is largest when direction of current is at 90-degree angle or right angle to the direction of the magnetic field. So when magnetic field and the current, they are 90-degree direction with each other, or they are at right angle, at that time the force exerted is maximum, and that is demonstrated by this experiment. So you have to remember only that the direction of force on the conductor changes when direction of current changes and when direction of magnetic field changes. And what is the magnitude? Now we have to decide two things of the force. One is direction of the force and another one is magnitude of the force. Magnitude meaning how strong force is or how less it is. So direction is decided by this 2 points, and magnitude is maximum when the current direction and magnetic field direction, they are at 90 degree with each other. At that time magnitude is maximum, and when their angle gets reduces, then the magnitude will get reduced, and magnitude will become 0 when these two are parallel. That is, direction of current is same as direction of magnetic field. At that time the magnitude is 0. So that is about this one. So then we have to understand what is Fleming's left hand rule. Now all these three directions are determined by Fleming's left hand rule, and there is Fleming's right hand rule also, which is applicable for magnetic induction. And since magnetic induction is cancelled or removed, so that is not there. Only you have to know Fleming's left hand rule. So Fleming left hand rules, see here, the left hand is taken and three fingers, that is thumb, middle finger and forefinger, all three are stretched so that they are perpendicular to each other. If the first finger points towards the current, the second finger points towards the magnetic field, and then the thumb will point towards the force experienced by the current carrying conductor. This is how it is. Okay, so this is the thumb rule, and from thumb rule you can decide if the two directions are given, third direction you can find out. So that was about thumb rule. And magnetism is used in medicine. So our brain and heart, they give you magnetic impulses most from our body. So magnetic impulses all over body, but the brain and heart, they give most magnetic impulses. So for example, for images in medicine, like for example MRI, magnetic resonance imaging, this is used. MRI is used in diagnosis, for medical diagnosis. So that is about the magnetism in medicine. And we have to understand only two things of electric motor and electric generator. One is conversion and another one is principle. So electric motor converts electrical energy into mechanical energy, and electrical generator converts mechanical energy into electrical energy. Both these works on the principle of Faraday's law of electromagnetic induction. Both works on the electromagnetic induction principle. So with that, we will discuss this very last part of this topic, that is domestic electric wire or domestic electric circuit. This part is again very easy. You don't have to remember much things. This is all general. So how the supply wire comes? There are three types of supply wires. One is red insulated, which is called a live wire or positive wire. Another with black insulation is neutral wire or negative wire. Third is green wire, a green insulation wire, that is earth wire, and this earth wire is connected to the metal plate deep into the earth. You must have seen earthing at your residence. So that is the earth wire, and it is black in color, sorry, green in color. It is green in color. And what for it is used? Earthing wire is used for safety for those appliances having metal bodies. So metal body appliances, we hold them or we touch them. So for example, toasters, fans, fridge, and so much. It provides low resistance path for flow of current. That means if the metal part is electrocuted, then the current will pass into the earth instead of flowing through us into the earth, and we are protected. It will prevent getting shock in our body. So that was about green wire. And potential difference or the supply voltage in India is 220 volts. And with that, let us see the sequence, how the power supply comes. Power supply comes from overhead lines which are running from the poles or underground cables, and from there it comes to the meter board, and at the meter board it comes through the fuse or circuit breaker, then it goes to the meter, then it goes to the main switch, and from the main switch there will be two wire circuits. One circuit type is 15 ampere, that is for higher power, which uses geyser, air coolers, ACs, and etc. And other ones are of capacity or rating 5 amperes, for example bulbs, fans, etc. For each circuit there is on off switch to each appliances. Now potential difference or the voltage are equal in each appliances, so that is why all these appliances are connected in parallel. So that is all about the domestic wiring. So last we are discussing about the electric fuse. So let me go to the last part, that is electric fuse. See, there are two protections we are discussing here. One is earthing and the second one is electric fuse. So both has got different type of protection. Earthing has a protection from shock, whereas electric fuse is a device which prevents damage to the appliance and the circuit due to the overloading. When the circuit is overloading, that means current inrush in the circuit is very high. And if the high current is there, your electrical appliances will get burnt. So to protect that, electric fuse is used. And another thing you have to remember, how overloading occurs. Overloading meaning more current flowing. What happens is, one case, live wire and neutral wire comes in direct contact, and that we call short circuit. So overloading occurs when there is a short circuit. This is short circuit. When live wire and neutral wire get touch each other, it is short circuit. There is fault in the appliance, then also very high current comes. Short circuit, again I have listed it here. This short circuit is listed here. It is due to accidental hike in voltage. Then too many appliances are connected in a single socket, then also overloading takes place. These are all the conditions when overloading occurs. And the last thing is Joule's heating of fuse. Fuse material is used having material of low melting point, but it should be a good conductor. So it is rated for so much of current. When the current exceeds the rating of the fuse wire, Joule's heating takes place, and Joule's heating takes place is I square RT. So this much heat is produced and fuse wire gets melt, and that is how the circuit is disconnected. And that is all in this topic.
We at eLearning Career Academy are running classes for standard 9 and 10 in maths and science, and also for standard 11th and 12th in physics, chemistry, mathematics and biology in offline as well as online mode using memory techniques. Here are the links for joining these classes. These links are also given in the description of this video.